let's finish chapter 8 by mentioning this final remark. At the end of the last lecture, so we mentioned that this, the radius part of the hydrogen wave functions shows the probability distributions as function of r squared times the radius part of the eigenfunction square, capital R squared. And you can look at the probability distribution as function of the radius part of the variables and see called the electron orbits, the shapes of the electron orbits in the hydrogen atom. So for example, in general, we know that this H function is a polynomial of the degrees nr, where nr is given by m minus l minus 1. It in general has this nr nodes or zeros. So when this capital R vanishes as function of r, and we call this zeros or nodes. When these probability distributions reach some maximum value as function of r at particular radius r, and we call this bumps. So of course this probability distributions shows many bumps and nodes, okay, as function of r. And we'll see different cases when we talk about these bumps and nodes. So in general, this probability distribution shows this n minus l bumps or nr nodes coming from this polynomial H function. How do we get this? Well, you simply just calculate this probability distribution, which is r squared times capital R squared, little r squared times capital R squared, okay, in the three-dimensional space. Suppose we consider this little l is this just n minus 1, which is the maximum value of L, right? So in this case, L is n minus 1, so you simply plug in here, and we get to this probability distribution. In this case, you take the differentiation of this probability distribution with respect to R, and you get either maximum or minimum, but you can simply just plot this function and see this is really a maximum value at this distance R, which is given by this n squared times a0 divided by z. This is what you have learned in the Bohr series, that the electron radius circling around nucleus cores in the hydrogen atom in the Bohr series is really this quantity right here. Remember that, which corresponds to this maximum value of angular momentum L given a fixed principal quantum number n. But here we derive this simply by finding this maximum point or the bump positions of this probability distribution. This is obtained purely quantum mechanically. So in general, we could find this tendency or trend of the bumps and nodes that for a smaller value of L, meaning the smaller the angular momentum quantum number is, there are more bumps. As a result, the orbits are not circular. It's more like elliptical shape for these orbits. And you can see from this plot right here, so all those different colors of the plot are the probability distributions of different principal quantum number, but the angular momentum quantum number L is all 0 here. So for all L equals 0 curves, you can see that the more the n value is, the larger the n value is, you get more bumps and nodes. If this little n is simply just 1, you get simply 1 bump. But if little n is 2, you get 2 bumps, 1 node, and so on. Okay, so as you increase your orbital angular momentum quantum number L to a larger value, and you find that the number of bumps decreases. For example, n is L equals to 2, but n equals 3, you get only 1 bump, which means that the radius that corresponds to the maximum of the probability distribution is just a fixed R0. just one radius. So if you look at this maximum of the probability that you can find a particle around this hydrogen nuclear core, and this is precisely a circular orbit. Okay, so this is the place where you can find the particle with the highest probability. And of course, this is not a single kind of a classical orbit, because this is all about the probability distribution. Remember that. So around that orbit, you have also a finite probability to find the electron. But there is only one maximum here, indicating that this kind of a probability distribution shows a circular symmetry. Like this, you could circle around this orbit, you find the maximum of your probability distributions is precisely at this radius. And so this is a three-dimensional shape of so-called orbit. So there's no orbits in quantum mechanics. The only thing we have is a probability distribution. But if you connect the maximum of your probability distribution, and it looks like a circular orbit, but it's not a circle. Remember that. But if you look at this, say, all these multiple bumps curves, you can see that the maximum value of this probability distribution is not restricted just to one radius, but there are more than one. Say R1, and this is R2, which means that the probability of finding the particle around this nucleus core is non-circular shape, which means that you may find sort of electron orbits as elliptical type, meaning that you have two different radius, R1 and R2, with a maximum probability distribution. And so this indicates that this kind of so-called orbits are not circular type. And so on and so forth. So you can try to make a plot, a cartoon picture of this, say, if we have these three bumps. How can you imagine we have three different radius? Well, is it really an elliptical shape? No. Circular? No. It's a very complicated shape. There are three different orbits. I don't know how to draw that. So you can see very clearly that this kind of a Bohr's naive picture of circling around this nucleus core in the hydrogen atom is not the correct picture. So the correct way of looking at this Schrödinger eigenfunction is precisely this type of calculation, that we should look at the probability distribution of electrons, and in the three-dimensional space, what we have is what the electrons should behave. So number three, the radius part of the probability distribution shows this kind of properties. So you have this kind of distance. But you know that the total wave function, eigenfunction, is a product of this YLM and this capital R. As m increases, the probability distribution goes like sine theta, this PLM square, as we mentioned in this spherical harmonics. And when m is actually approaching this maximum value, which is L, then this PLM function, as function of cosine theta square, behaves as sine theta to the power of 2L. But when this happens, this is maximized when theta is pi over 2, because the maximum value of sine theta is 1 when theta is pi over 2. When that happens, this YLM is actually peak at the equator. If you look at this sphere and this equator, which indicates that the theta is actually pi over 2, with increasing m to to the maximum value, which is L, then this angular part of the eigenfunction is actually maximized at the equator. And the width of the peak width, also decreases as you increase the value of L. This indicates that this kind of angular momentum in the very large M and L limits looks very similar to the classical planar orbit. To see this, you could actually look at the classical limits of angular momentum vector. That's, for example, if you consider that you could actually make object a circular motion, and the angular momentum is actually pointing to the z-axis in the classical system, right? And your total angular momentum in that case is just Lz in the classical limit, which is exactly what happened here when L is very large and when n approaches the maximum value of this possible value, which is L. The probability distributions of this quantum mechanical, say, object, which is electron, wave functions, is actually a peak right at the equator. Right? So if you look at this equator, you'll find that the probability distributions is actually all maximized around the equator. So it looks like you don't have any probability to find the particle elsewhere. If the quantum mechanical object is distributed such that you cannot find it other than the equator, then this situation is very similar to the classical mechanics, where you simply just make a moving object doing this kind of circular motions with the angular momentum pointing to the z-axis. But of course, we need to bear in mind that this is not a 100% accurate description, because we don't have the situation where you have 0 Lx and 0 Ly, but finite Lz. Strictly speaking, all these three components of angular momentum operator or vector in quantum mechanics should survive. Even in the classical limits, we can only say that this Lz is much larger than Lx, Ly, but both either Lx and Ly cannot be 0. But you can look at this probability distribution both in the radius part direction and also in the angular part by looking at this YLM. So let me just make some sketch of this angular part of this distributions. For example, this is xc, and this is what y00 squared. This is YLL squared, and so on and so forth. You could look at your textbook. If n is maximum value L and L is large, you could very easily see that the probability distribution is centered around this equator, which is this direction right there. Okay, is that equator. But for a more complicated shape of the spherical harmonics, please look at your textbook. So let me just show you these pictures in our textbook, so I won't bother making all these plots. Right, so if you look at your textbook, page 141, you can see all these beautiful shapes of this spherical harmonics. If you plot this YLM square against this angular variables, and you'll see all this kind of a dumbbell shape or a circle or a butterfly or any fancy shapes or general M and L. And those different orbits corresponds to all these different electronic configurations that you are familiar with in, say, high school chemistry. For example, this s orbit and p orbit and d orbit and so on. So let me just write down this kind of the name of the electronic configurations that you are familiar with when you are in high school. When L equals 0, we call the s orbit. When L is 1, it's p, and L equals 2, we call it d, and f when L equals 3, and g for L equals 4, and h for L equals 5, and I for L equals 6. When you fill out this electronic states in any realistic atoms or chemical compounds, you start from the lowest angular momentum variable. Also, you start from generally the smaller principal quantum number. You start to fill up all the electronic states. So let me just remind you of this, the order of the electronic configurations, which you are familiar with when you fill up electron states in all these atoms and molecules and solid state materials, starting 1s and 1p and 1d and 4s and so on and so forth. So you can see there are some exceptions when you start to fill up this electronic states from this lowest quantum number and lowest value of the L. For example, the states 1f is actually higher than this states 2s, and so on and so forth. You could find all these exceptions, and this is because those inner shell electronic states may have higher energies than this outer shell states, because the electrons are more closer to the nucleus core, which enhance the Coulomb repulsion. Okay, as a result, some of these inner shell states may actually have slightly higher energies than some of the outer shell state with smaller L. And that's the origin of what you remember when you were at high school, to memorize all this kind of electronic state configurations. And this is the reason why you have such a kind of ordering in this energies profile when you try to fill up all these electronic states, like this, and so on and so forth. In general, you now can understand at least hydrogen-like atoms, their eigenstates and their wave functions, probability distributions of these wave functions in three-dimensional space. So let's take a short break. When we come back, let me just make a final remark regarding these degeneracies that we discussed previously. Yes?
老师，不好意思，可以问一下最右边黑板 L，M 绝对值趋近于 L， 然后那一行怎么来的吗？
You simply just look for this special function PML, PLM, when M is approaching L. And you look for your textbooks. So PLL is function of the cosine theta, is actually sine theta to the L. And you square this, you get this. Yeah, good. So let's take a short break. Try to think about all these problems and try to understand all this very counterintuitive quantum phenomena that we discussed in class. And in terms of your own language, how can you understand this? Okay, so this is probably the most important part of the class. And the remaining part is some simple calculations, the Dirac notation and so on. So let me just make a final remark regarding this large degeneracies of this hydrogen problem. Remember, we have checked that this degeneracies of this eigenstates of the hydrogen atom is given by n squared, where n is the principal quantum number. Remember that. So we simply just sum over L from this 0 to maximum value, 2L plus 1. Remember that this is what we have discussed some time ago. Degeneracy in hydrogen atom is given by the square of your principal quantum number n And when n goes very large, this degeneracy is huge, because when n equals 3, you get 9 degeneracies, okay, degenerate states. When n equals to 10, you get 100 degenerate states for a fixed value of little m. So why is that? So our textbook reminds us that the reason why we have a very large degeneracy in the hydrogen atom is because of the 1/r potential. Suppose that the Coulomb potential is replaced by a different type of potential, which is different from 1/r potential, then we may remove this degeneracy. And the reason why this 1/r potential leads to such a huge degeneracy is because of additional symmetry emerges. This additional symmetry is actually described by this additional operator, which commutes with Hamiltonian. Remember, we have these 3 operators that are mutually commuting with each other. So the Hamiltonian and L square and Lz. But for the 1/r potential, we have additional operator, which can actually be included in this commuting set, which is capital A. And capital A is defined by this operator, which is a combination of L cross P minus P cross L plus this unit vector of r divided by this radius, distance r. Okay, so if you plug in this commutator of H and this operator A, and you will find that this commutator vanishes. Remember, whenever we have a vanishing commutator, there is a constant of motion. Remember that. That is because we have the Heisenberg equation of motion. This is proportional to this, say, dA by dt. So if dA by dt is 0, which means that this A operator, if you measure this quantity in a Heisenberg representation, it stays constant. Okay? It is independent of time, which means that you have a conserved quantity. Whenever you have a constant motion in classical mechanics, you know that there is a conservation of something. So if the angular momentum is a conserved quantity, then you have a conservation of angular momentum. If the momentum is a conserved quantity, then you have a conservation of momentum. If A is a constant of motion, then there is a conservation laws associated with that A operator, which we don't know what that is. It's a very complicated object. But then you can imagine that now we should include this capital A operator as the additional operator in the commuting set, and there will be simultaneous eigenstate of all these 4 operators. And in that case, there's a chance that indeed this happens when we have additional operator which belongs to the commuting set. Then we have many degenerate states, more degenerate states that you could imagine because of this. But we could remove that degeneracy by considering additional terms in this potential. So we could see this very simple example of such additional term that you could add to your 1/r potential to remove the degeneracy, which is this type 1/r squared. Suppose I add this additional term to my Coulomb potential energy, which is 1/r squared times some prefactor. We could plug in this to this Schrödinger equation of hydrogen atom, and then we could simplify this equation, and we'll get exactly the same eigenfunctions. The radius part of the equation looks the same, except we need to make a little bit modifications. Remember, there's a term proportional to the L times L plus 1 divided by r squared. If we plug in this y or m to this Schrödinger equation and extract this radius part of the Schrödinger equation, suppose I add this additional term, which is again very similar to the 1/r square term, then I could simply just replace this L by L star. Where does L star is related to L by this formula. Okay, so you can show that if I plug in this additional term to the V of R potential, you could simplify the radius part of the Schrödinger equation to this form, where the L star is given by this relation to L. So L star times L star plus 1 is the same as LL plus 1 plus G squared. G is given by this coupling constant right here. Okay, so you could very easily verify this. If this is the case, you could really solve this L star, which is this quantity. You plug in this L star back to this, say, eigenenergy. So the original eigenenergy with 1 over r potential only is actually inversely proportional to this little n squared. Remember that in the denominator. But now you should revise it. If you add this additional term, proportional 1 over r squared, to this potential, now L should be replaced by L star, when L star is given by this. So now, remember, L star should be here. L should be replaced by L star. So if I do so, then my new eigenenergy is given by this thing, which is nr plus 1/2 plus square root of L plus 1/2 square plus G square, everything square. So now if you look at the new eigenenergies on the right, you will find that this is no longer degenerate that much, because now the eigenenergy depends not only n but also L. But previously, before I add this term, this eigenenergy depends only on the principal quantum number. Remember that. So this depends only on n, but not L. As a result, for different L's, you get the same energy, and that's the source of the degeneracy. Does not depend on L. But here, so once we add this 1 over r square potential term in my problem, then the eigenenergy does depend on both n and L. Remember that. So this is given by nr plus 1/2 plus the square roots of this complicated object, which depends on L. So now the degeneracy is splitted, it's lifted, it's removed. Because for different L, you get different eigenenergies. Even if this is the same principal quantum number n, but here, before I introduce the additional term for different L, as long as n is the same, you get the same energy. But here, it also depends on L. For a fixed n, L is different, then the energy is different. So that previously degenerate states are removed. This E n now becomes E tilde n L. L1, L2, and L3. Okay, so this is just some kind of a remark that you need to remember. So nature really helps us to have such a huge degenerate eigenstate of hydrogen atom, because our Coulomb potential is very simple, which shows additional symmetries. So far, so good. Any questions? Yes.
这个部分是在讲说在处理不是对称的物理系统的话，就没有讲变态，要怎么处理？
Well, you need to again go back to Schrödinger equation if you have less symmetries in your problems. But there's no general rules to solve the Schrödinger equation in the more complicated potential. And even in this case, I can imagine I could add, say, 1 over r cubic term. What will happen? I don't know. You can try, and you could get all different sorts of lifted degeneracies if you have different potential. Fortunately, most of our, say, quantum systems have such a simple Coulomb potential. There are not so many cases where this additional term should be introduced. Okay, so that's the lucky thing we have. However, there is no guarantee that someday you may figure out that your effective potential, in addition to the Coulomb type, should include another type, and which will complicate it further. Of course, this will not be kind of your homework or exam problem just to lift the degeneracy by a really complicated potential. Don't worry about that. But bear in mind that the huge degeneracy comes precisely because of this higher symmetry of the 1 over r potential. If the potential is changed to different form other than 1 over r, then we need to remove, this degeneracy will be removed or lifted. Okay? So this is the whole point of this remark. But regarding how to handle this very complicated situation where we don't have simple 1 over r potential, well, this is still an open problem. Okay, so I don't have a general answer for your questions. So guys, that's the end of the chapter 8. On Wednesday, we'll start chapter 9. So I'll see you on Wednesdays.